All of the reactions we talked about in part 1 rely on enzymes. This graph demonstrates the addition of an enzyme to a reaction with that green line showing you the path with the enzyme. Enzymes are the catalysts of living things. They do what all catalysts do. They lower activation energy by creating an environment that is optimal for the reaction, so it needs less energy to move forward, less activation energy. So you've got your original energy moving to your lower form of the energy, so there's your activation energy without, and your activation energy with the enzyme. So much slower, so much simpler. Here's how an enzyme works. When reactants, which we're now going to call substrates because they are working with an enzyme, those reactants or substrates bind to the active site of the enzyme. And the enzyme changes conformation or shape. Slight shifts in shape can put tension on the bonds that need to be broken and align the molecules or the parts of the molecules that need to bond. Once bonds have broken and formed, the product is released. Now, enzymes can often run reactions in both directions, turning the product back into reactants. So, the reactant to product ratio does factor into the speed and direction of these reversible reactions. If left alone, a single reversible enzyme could bring the reactant and product into dynamic equilibrium, but often enzymes are working in a complex organism with many enzymes, and these enzymes actually work in these interconnected links called metabolic pathways, where each enzyme consumes the products of the previous enzyme, and that drives a forward reaction. So products don't build up until they are the final product that's needed by the body. Metabolic pathways are amazing. They involve many enzymes acting on a related series of substrates. So enzyme 1 creates a product by consuming A, and enzyme 2 will use that product as a substrate by consuming B. As enzyme 2 consumes product B, enzyme 1 keeps feeding it with more of B. B should never build up because it's being turned into C. Thus, the enzyme will mainly work in one direction. So what are you left with at the end? You should be left with D. That is what is amazing about metabolic pathways. They move very complicated, multi-step processes forward in cells that are jam-packed with lots of enzymes, lots of substrates. They're very, very crowded, but many processes can happen at once, and very specifically and very targeted processes can happen depending on which enzymes are present at the time in the cell. These are the 4 primary features of enzymes. They speed up the rate of reactions. They're not consumed, thank goodness, so they just continue to do their job. They often work in both directions, and they're highly specific. They should only bind to and recognize specific substrates for the process they're involved in. Other factors that can influence enzyme reaction rate are temperature, pH, substrate or reactant concentration, the presence of coenzymes and cofactors, and the presence of inhibitors, regulators, or activators. All enzymes operate with an optimal temperature and pH, so taking the proteins out of their optimal range denatures them and makes them increasingly ineffective. Sometimes you can restore their optimal range and they go back to a fully functional protein. So denaturing can be reversible, but that process can be detrimental as well. So if you're looking at these graphs and the rate of reaction, that's telling you how fully formed that shape is or how denatured it is. This is like when I taped your fingers in the enzyme reaction game. I changed your shape. What is optimal to one enzyme may not be optimal to another. Sometimes enzymes like the Taq polymerase from Thermus aquaticus, that's a bacteria, can withstand temperatures of up to 95 degrees Celsius. That's nearly boiling. And it has an optimal range of 75 to 80 degrees Celsius. Humans use this enzyme to our advantage in some of our biotech processes. But most of our human enzymes, again, are going to be operating at human body temperature, which is in the 20s, like 27 degrees Celsius. Here you can see the pH ranges of two enzymes. These enzymes are suited to different parts of the body, obviously, the intestines versus the stomach, where pH is much lower. But I want you to look at the shapes of these curves really quick. pH, the way it denatures and affects the rate of the reaction, is equal on both sides of the curve, whereas cold, you see the enzyme get more and more active with heat. That makes sense. Heat affects movement and kinetic energy as well. But then once you get past that optimal temperature, you can slope off very quickly because literally you're starting to cook that protein, very much like cooking an egg. So that's why you see the two different shapes there. Here you can see the effect of substrate concentration on the reaction progress. I disagree with this a little bit, but the higher the concentration, the faster you're going to reach your reaction progress. But I don't know about the low concentration moving up earlier than the medium. It's a little wonky. I bet if you thought about it, you could create a better graph. Coenzymes and cofactors are required for some enzymes to function, and they'll speed up the rate of others. The difference is that coenzymes are organic, and cofactors are the term for inorganic versions. So often these molecules serve as electron transferring agents. So you've got an oxidized form here, a reduced form here. So one can accept electrons, one can donate electrons. And again, generally whenever you're picking up electrons, you pick up hydrogen protons to balance that out. Coenzymes and cofactors can also move small functional groups around. Just depends on what's needed and what their structure is. One example is NADP, which is nicotine adenine dinucleotide phosphate. You should be able to look at it and see that it appears to be like a nucleic acid. It is organic, so we would call it a coenzyme, and its role is to transfer electrons. Iron, those Fe ions, are required by ferredoxin during photosynthesis. Iron is also required by hemoglobin and catalase, so a lot of enzymes require iron to function. It's metal, so it is a cofactor. It is inorganic. And I am greatly oversimplifying the coenzymes and cofactors right now. I just want you to have a few examples. I want you to know that generally their job is in transferring electrons to those oxidation and reduction reactions that we are not going very deeply into. So if you decide to go more deeply into this in future courses, you'll get a lot more detail and it will probably start to make a lot more sense. Inhibitors can be competitive or allosteric. Note the difference in where the inhibitor binds. You've got one binding into the active site. It is competing. It's the competitive inhibitor. You've got one binding away from the active site. It is non-competitive or allosteric. Inhibitors of all sorts are used in modern medicine. ACE inhibitors are a class of blood pressure medications. They reduce blood pressure by actually keeping an enzyme from making a molecule that makes your blood vessels get tight and constricted. So keeping those blood vessels relaxed lowers your blood pressure. We're constantly using this. We use it in antibiotics. We use it in HIV therapy treatments. so many of our medicines result from finding inhibitors for certain enzymes that are necessary for those microbes that are making us sick, or even our own enzymes that are making us sick. So here again is allosteric inhibition. You can see that when the inhibitor is off the enzyme, it is able to interact with its substrate, but allosteric enzymes are not always inhibited enzymes. Sometimes they are actually activated or regulated by something that is binding away from the active site. So that term allosteric, we're just talking about binding away from the active site. So here, unless the activator is present, the substrate cannot bind. So with the activator, then you have an active enzyme. All of these various ways of regulating enzyme activity is our body's way of maintaining homeostasis, because as maybe a substance builds up in the body, that substance can actually help turn on enzymes that are going to help break it down. So very helpful, very much related to homeostasis. My final note about inhibition is how both inhibition and metabolic pathways can be utilized by living organisms to control entire processes. This allows for negative feedback loops. So the process itself shuts down once it's accomplished its task. So this is again feedback inhibition. In other words, more of a final product reduces the overall process. So it's like a heater. Once you have enough heat produced, that heat is the signal to shut off the heater. So that's called negative feedback. In an organism, this again helps maintain homeostasis. So great to be a living thing. Our body is just constantly doing these processes for us. We have the high concentration, and it shuts off the enzyme. It's very efficient. It's amazingly efficient, considering how many things have to be done by our bodies. So as a final silly note, if you're ever having a bad day or you're feeling gloomy, at least you can be happy that your body is able to fight entropy with anabolic processes that are catalyzed by enzymes using interconnected metabolic pathways and negative feedback loops.